I'm John Wilker, the organizer of 360 IDEP. I hope you enjoy this session recording, but first I wanted to mention one thing. We've served the community since 2009, and over the past few years we've had to take on debt in an effort to keep the conference alive. After several unforeseen challenges, not the least of which is a pandemic of indefinite duration, we've had to make the hard choice to end the conference as we're now facing over $100,000 in debt. As a result of requests from the community of how they can help, we've created a GoFundMe campaign. If you're inclined and able, please consider donating to help keep 360 IDEP going. The QR code after this will link you to the campaign. Thank you. Enjoy the recording.
Hello. Welcome to a discourse in humane development. I'm Jill Scott, and I'm really excited to be speaking in front of people because there's something really appropriate about leaving my comfort and my cats for just a little tiny bit to communicate with people about how important it is to communicate with people. And ultimately, that's what we're doing as developers. We're communicating. And one of the primary ways that we're doing this is through code. And how do we do that well? It's a concept that Mark Seaman, in his book, Code That Fits in Your Head, he referred to it as humane development. And I like to describe it as programming for the human brain. This is my favorite slide. It's pretty succinct. So I'm going to start this presentation like I start most of my days, with toast. So sometimes in the morning, I eat toast. And sometimes in the morning, I find my place super tidy, and all the cords picked up, and the cat toys away, and I'm super lying, because that never happens. But on the rare occasion that it does, I let my Roomba whir to life. And sometimes I'll dust off my hands, and I will let the little crumbs fall in front of the robot that I have affectionately named a Rosie. This is Rosie. She's seen better days. Don't judge her. It's not her fault. She didn't know I was going to be taking pictures. So sometimes when I drop my crumbs and I let her sweep them into her little spinny maw, I'll imagine, depending on my mood, either that she is kind of purring in delight at receiving a treat, or else that she is darkly grumbling about her existence built to serve. But the truth of it is, Rosie doesn't care. Rosie's a robot. She's going to dance around, she's going to sweep, and she's going to gobble, regardless of where I drop my toasty bits. She doesn't really recognize my existence unless she bumps into me, and she doesn't have pronouns. She doesn't even know her name is Rosie, even though her app does. And the truth of it is that computers don't care about us, and they don't care about whether we care about our users. They don't require us to build accessible apps. We can add safeguards and all the warnings that we need to alert us if we fail to include dynamic text, if we fail our contrast tests, et cetera, et cetera, et cetera. There's a slight delay from my iPad to this, so it's throwing me off, and I apologize. Our tools only care about these rules if we care about these rules. And there's a reason that we struggle for an embarrassing amount of time to get auto layout working on the largest text size. I'm so sorry for that screenshot, it's atrocious. We do care about our users, and accessibility matters. And often that's where we as devs think that the story of humane development ends often, is with the end user. But the thing is, if there is an end user, it's because there is a beginning user, and that beginning user is also human. It is us, it's the developer. It's the dev writing the code and the dev reading the code. And as sometimes those are one and the same, right? The dev reading and the dev writing are often the same person, but as we all know, it doesn't mean that the dev writing is going to be able to make heads or tails of it later. And that's because humans are imperfect. But we humans are the ones manipulating code, and it's important that we acknowledge not only our limitations at the exact moment of writing that code, but also the very human limitations of those who are going to be reading that code a few months down the road. And that's even if that person is you. And imagine this is a real mirror and it's reflecting you back at you. It is super profound. I can't do that on a slide, but it's really cool in theory. So let's move on to memory in the brain. To understand how we process the code that we're reading and writing, I'm going to talk to you about 3 different kinds of memory. And that's short-term memory, long-term memory, and working memory. So we're going to start with short-term memory. And I'm going to ask you to read these 2 lines of numbers in your head. Just take a second to do that. You don't have to do anything with them, just read them. So now imagine that I asked you to recite those numbers back to me. And think about how many you could name. And if you're anything like me, not more than a few, if any at all. There's a limit to how much you can keep in short-term memory. I'm going to continue to refer to these pieces of information as chunks. We're going to talk about them later, but in short-term memory, the point is your chunk capacity is limited. Experts say anywhere like from 5 to 9. It's kind of a guess. It differs in every human. A lot of people say like the magic number is 7, but it's different for everybody. So I'm going to stick with 5 to 9. And although you may remember a few of those numbers right now, you're guaranteed not to remember as many in the minutes to come. And that's because with short-term memory, retention only lasts for a few seconds. And as time passes, you start to forget more and more of the information that you previously consumed. And this is referred to as temporal decay. It's another key characteristic. And forgetting, in that sense of temporal decay, is essentially immediate. So by the nature of short-term memory, you're not going to be able to hold it around unless you convert it into long-term memory. The chances are, if I ask you in 12 slides to tell me the same numbers, if you could even remember them right now, in 12 slides, you're certainly not going to be able to, unless you're actively trying to retain them. And that's because access to short-term memory requires conscious attention and requires conscious effort. And you have to be purposeful in remembering the information. So you might actually be able to feel the cognitive exertion that's required to try to access those pieces that you placed in short-term memory. If you knew that I was going to ask you to repeat them, it's possible that you would have repeated them over and over again in your head, and maybe you did. But attention is really fickle. It's a really fickle thing, and you can't just flip it on and off at will. And maybe you did dedicate your attention to the numbers because you knew this was a talk on memory, and you're like, oh, she's about to ask me to repeat those numbers. So maybe you can recite the whole first line because you're that good. But maybe you stopped paying attention while you were reading them, and that's 100% what I would have done. Maybe you were distracted by the title, and you're like, why is there a title here? Why is it all capitals? Why is the kerning so, anything could distract you in the moment. So maybe you can't even tell me the first 2 numbers, and that's 100% okay. That's really normal. There's plenty of other characteristics that I could talk about when it comes to short-term memory. Things like the fact that short-term memory doesn't actually cause any physical changes in your brain to encode that information. But these are the main ones that I'm going to focus on because they relate most to our work as developers. And they also differentiate it, there we go, from long-term memory. So I'm going to give you a second to do this activity. Just try to name 10 states or countries as well as their capitals in your head or out loud, I guess, if you want to. I'll give you a few seconds. Just try to see how many you can get. So I want you to try to notice how accessing that information felt, what it involved, and how it was different from accessing the numbers, for example, on those 2 lines. Most likely, you learned your states or your countries and your capitals in elementary school, and you haven't encountered them very much since. But you have encountered with regularity since then the states and the countries and the capitals that you kind of encounter on the daily, that you encounter in the news or whatever. But maybe you haven't encountered some of those facts lately. Maybe you still recall that Juneau is the capital of Alaska without having actually encountered that fact very often since. And this is one of the prime characteristics of long-term memory, is that retention is for minutes to years. It can last a long time. And forgetting is gradual. It can happen. For example, for me, I asked myself, what's the capital of South Dakota? And I have no idea, and I'm really sorry if anyone here is from South Dakota. I have nothing against the state. It's just, I haven't lived there. I don't know people that have lived there. I haven't run into that fact very often. And so it's like in there somewhere, it's in my brain, it's just not gonna return without some prompting. Memories deteriorate over time, but there's also no real limit to the amount of information that we can encode and we can store in long-term memory. It's essentially infinite. So think about how much information you drew upon to access those states and capitals. The pool of like geographical and maybe just factual knowledge has to be really vast. And retrieving it still probably didn't feel like too much of a strain, at least for the first few states or countries and capitals. That's because retrieval from long-term memory is mostly automatic. And remembering the capital of like the state or country you grew up in, it probably didn't require any thought at all. Sometimes effortful retrieval is needed, however. And you may experience that in remembering one of the capitals. So for example, when I think about Illinois and I try to retrieve the capital, I'm like, okay, it's not the first city I think of. It's not Chicago. And then I eventually remember that it's actually a city that I usually think of as the capital of like a whole bunch of other states. And then I arrive at like Springfield. I hope that's right. I actually didn't fact check myself. So while I take these bits of information from long-term memory and hold on to them and use them to try to like recreate this information that I retrieved, it starts to involve working memory. It's not a significant amount of working memory, but it allows me to put some effort into retrieval and reconstruction as necessary. And while that reasoning and effortful retrieval do involve working memory and sustained attention, it's like certainly nothing compared to short-term memory. So essentially very, very little dependence on attention unless you're doing a kind of reconstruction. And the real brain magic happens when we combine those two types of memory, when we combine short-term and long-term memory. And it leads us into the next topic, and it's perhaps one of the most important assets that we take with us to our job, and that's active working memory. So active working memory is basically the memory that you're engaging when your brain is doing work. As you load up your brain with chunks of information, it's your working memory that's holding it all and processing it. And it's manipulating the information as you need. So as you can imagine, it requires attention. It's more than short-term memory. It's more than just remembering a phone number long enough to write that phone number down. And it describes the use of attention to actually manage and do work with short-term memory. It's often referred to as just working memory, and I'll probably say them kind of interchangeably in this talk. But a lot of people call it active working memory to underscore that it is a process and it's ongoing. There's a very intentional nature and continued processing at play. So as is true of short-term memory, it's limited in capacity. And I want to point out here that like experts in memory don't necessarily agree on the definitions of active working memory and how it differs from short-term memory because they're so closely linked. But having kind of a working definition is really valuable for this talk in particular, having the ability to talk about active working memory in definite terms. So I'm going to continue to do that, but just know that that's a thing that's out there. Not everything's agreed upon, but in literature, it's pretty consistent. And it is known that active working memory is limited. And so a lot of what I found says it's limited to 3 or 4 chunks. And that's because there's cognition involved. There's like cognitive processes going on, and that necessarily means that it's more limited than short-term memory. It's easy to just store something for a second. It's much harder to it's much harder to remember it as well as manipulate it in your head, and that's why the capacity is less. And working memory doesn't only involve short-term memory. It actually provides an interface between short-term memory and long-term memory. So to perform work on the information that you have in short-term memory, you have to access long-term memory for the frameworks that you need to manipulate that data. It kind of tells you how to manipulate it and how those things fit together that you have in short-term memory. So that's why I call it an interface between the two. In doing these tasks, working memory has basically 3 executive functions. And those are inhibiting irrelevant information, shifting between processing and storage tasks, as well as updating old data. So in short, working memory is doing work. It's the real star of our jobs, and while short-term and long-term memory are essential and they're important, they're playing supporting roles to active working memory. I'm going to go over 3 models for understanding working memory. I'm going to kind of eliminate the brain as a computer because I'm 100% over time every time I practice this. I'll go into that in a second. I'll probably just speed through it. But let's start with the arithmetic example. So imagine I give you a simple arithmetic problem. Imagine I give you, that graphic looks terrible big. I'm so sorry. So imagine I give you the problem 48 plus 12 plus 11. Oh, I also want to pause and say I have ADHD, and I'm going to talk about that more later, but you just saw it in action when I noticed that graphic. It fits into my talk. So I give you 48 plus 12 plus 11. The short-term memory's job is really simple. It's just going to hold those 3 numbers, that whole arithmetic problem, in memory. And it just needs to remember them long enough either to write it down or in this case, to perform some kind of work on them. Then comes in long-term memory. And so that's going to be kind of the more ingrained stuff. That's like addition facts, what the plus symbol means, how to actually add numbers together. And then there's your working memory. It's going to use your long-term memory and apply that to the numbers that you have in short-term memory. So in this case, we probably can look into our long-term memory and retrieve that. It's going to be easy to add these 3 numbers together if we add them 2 at a time. So we do that. Our working memory lets us add 48 plus 12, and we store the result in working memory. So we store 60. Again, I haven't fact-checked, but pretty sure. So the result is 60. We can replace that 48 plus 12. We no longer need it. And as I said, one of the executive functions at play is updating old data. And we don't need that piece anymore. So we're going to update. And now we're left with just 60 plus 11. We can do that pretty easily, arrive at 71. And it's all thanks to working memory. This is the one I'm probably going to cut. It was already kind of intimidating to present because like the model is sort of imperfect. And I was a little nervous about presenting it in front of, fellow engineers that would be like, actually. So yeah, I'm going to cut it, but I'm going to run through it really fast because I do think it's helpful for kind of envisioning the difference between the processes of the different working memory. So short-term memory is basically RAM. Long-term memory is basically storage, your hard drive, your SSD, your NVMe, whatever you have. And your working memory is kind of a processor. And the thing I do want to point out about this slide, without going too much into detail, is that working memory is a processor, but it's also a process. It's always ongoing, and that's why it's referred to as active working memory. This model comes to you courtesy of Dr. Scott. She is my mom, and she's also a killer psychologist. And she's not like a killer psychologist, but she is really good at her work. So imagine working memory as a tabletop. And so you have to perform some tasks. You have a table. I'm going to get back to that in a second. You've also read a bunch of books on the topic. You've printed some code maybe that you wrote to help illustrate it. You've just consumed a lot of information. You know your stuff. And that represents your long-term memory, because you're going to use that to provide a framework for how your talk is going to go. I'm 100% using this talk in my preparation for it as an example, if that's unclear. So second, you have your working memory. And this might be some notes that you took, some new books that you bought, anything that you're going to actually use and that you still need references to, and that you're going to manipulate to put your talk together. That's your short-term memory. And like I said, your active working memory is the tabletop itself. And so you're going to use that to manipulate things. And every time you put something on the tabletop, you're storing it in your working memory. You're getting it loaded and ready to work with. And then you're continuing to use the stuff that you've already kind of consumed. And you're going to use that to kind of inform how you manipulate the data and how you fit it together and how you fit it into your talk. But be aware, and this is why I really love this model, the more stuff that you put on your tabletop, the more cluttered it continues to become. So your tabletop can only hold so much and still remain functional. Eventually, it's going to get too cluttered to actively, to be able to work on. And maybe stuff even starts to fall off. You have new piles of information and stuff gets pushed off the table. It's onto the floor. You no longer can use that in the moment while you're trying to use your active working memory. Your working memory can only do and hold so much. Why do we care? So this is a pretty important question. You may be asking yourself, why are we talking about memory at a mobile dev conference? And as you can probably already see, or at least if you believe me, as I've already said, working memory is one of the greatest assets to us as developers. It plays a really significant role in our day-to-day work. And that's because programming and software development as a larger term, it constantly taxes our working memory. We all have to hold and process so many interconnected pieces of logic and manipulate them in order to arrive at a larger goal, whatever that goal may be. And not only are we constantly beholden to every human's working memory limitations, but constantly some of us are experiencing greater limitations than others when it comes to working memory. And when developing, presumably we're all accustomed to writing accessible apps, to keeping in mind the end user, and striving to make their experience as seamless as possible. But I want to remind you that accessible apps, besides being a must for the end user, also are really important to the people that are in the process of using it. So don't forget to make the app, which is the code base in this instance, accessible to your colleagues and to your future self as well. So I'm going to talk about some of these conditions that I'm kind of referring to. And for a condition to be diagnosable in the DSM-5, it has to have an impact on some area of your life. And for a lot of people, that is at work. It's most clearly seen at work, where we spend so much of our time. For developers, that means that it's often seen as impairments in working memory. So I'm going to list a few of these conditions here, and I'd be willing to bet that most of us can either relate to one of these conditions or have worked with someone that, knowingly or not, relates to one of these conditions. So I'm talking about things like anxiety and depression, bipolar disorder, deafness, other auditory impairments, traumatic brain injury, autism, dyslexia, ADHD, and other developmental and learning disorders. Each of these conditions can have anywhere from a minor to a significant impact on our working memory, on our ability to process and store information. This, in turn, is going to provide a really serious hurdle to development, especially if the code is already an obstacle in its own right. Supporting those with conditions like these requires that we do our best to make the code consumable, to make it as easy to read and to work with as possible. As someone myself, like I mentioned, with ADHD as well as depression, I can confirm that my working memory is a hot mess. I also kind of identify as like a memory doofus, and I don't think that's diagnosable. I don't think that's officially in the DSM-5, but I'll ask my killer psychologist mother. I'm so sorry, Mom. So sorry, I keep referring to you that way. Okay, so conditions like these are by no means the only thing that affects working memory. Wanting to support those who are diagnosably disadvantaged should be enough for us to want to make an accessible code base, but also people with those conditions are not the only ones that are going to benefit. Not only is working memory limited for everyone, but in fact it's extremely common for any of us to have some kind of working memory impairment at any given time. Working memory is impacted by various states of being, and you can probably guess some of these. Sleep and substances for one. I don't know if you guys have tried to do any like boozy coding. I've attempted it, thought it was a real good idea every time. But maybe you topple over the Balmer Peak a little sooner than you expected. And I'm wondering how effective you were. If you're anything like me, I couldn't get very far past repeating, like, what was I doing? What was the task that I was on? And there's other things that can affect working memory, like exercise, nutrition, even mood. Maybe it's just a Tuesday, and that's your worst day for working memory. It's kind of an exaggeration, but also not exactly, because we don't know everything that affects working memory. We just know that it's not constant. In fact, and I know this is probably really hard to read, details not important, there was a study published in Europe's Journal of Psychology that was titled, "Why is Working Memory Performance Unstable?" And they kind of explored, 21 different factors that affect working memory. And they wanted to find out, what the consistency was in literature supporting these things being, impactful on working memory. And among the things they found with significant support, consistent support in literature, were things like stress, things like age, brain stimulation, even dieting. And then just imagine these varied impairments that they found compounded with an existing condition like ADHD, or even like too little sleep. It's a working memory disaster, and I've been there. Probably some of us can relate to that. And these various conditions and states of being factor into our ability to process information, our ability to work with information. The resources we use up when we're using our active working memory and when we do work in our brains are referred to by the term cognitive load. So cognitive load refers to just the mental exertion required for holding on to chunks of information and processing them. But in other words, it's just the resources being used by working memory at any given time. Sometimes when we're holding too much in our working memory and trying to do too much, perform too many operations, and then also factor in, like I said, things like ADHD and too little sleep, we experience what's called cognitive overload. So that's the state in which we're trying to hold too many things in active working memory, and it causes a loss of information. It's when you've put too many things on your tabletop to actively, effectively be able to work with them. And you've undoubtedly felt it. I think probably everyone has. It's when you're walking around your house, maybe on Sunday, doing your chores, and you're like, okay, I have to do this task, but to do that task, I have to do this one before it, and to do that, I have to do this, but like, so-and-so, maybe partner needs the car at this time, so I have to work that into the schedule. And suddenly you're in the kitchen, and you don't know how you got there, you don't know why you're there, it feels really important, you know there was a task there, but it's gone. It causes information to be lost. It could also be talking with someone at work about maybe about a feature that you're about to implement and trying to work through what requirements there are around it. And maybe there's a lot of logical steps that are required. And the more you start talking, the more logical steps there are, the more things you have to account for. And you're like, hold on, before we continue this conversation, I have to write some of this down or it's going to be lost. That's also cognitive overload. It could be something as simple as trying to do some mental math. And I'm sure that we could all theoretically do this mental math. I don't know if I could, depending on the problem. But if we dedicate all of our attention to it, probably we can add like a whole bunch of numbers together. But imagining that you're tired or that your ADHD is like, I got other things to think about, surprise. You can't necessarily hold all of those in your short-term memory and then move them to your active working memory. And you might need to reach for your calculator app, and you might need to just punch those numbers in. Totally okay, totally normal. It doesn't mean that you're not able to do math in your head. It just means that you're experiencing cognitive overload. So cognitive overload is going to happen. It's inevitable. And luckily for us as developers, there are ways to mitigate it. And it becomes pretty clear if we look at the two types of cognitive load that we experience. So one of these is called intrinsic cognitive load, and it's by definition inevitable. It's the necessary cognitive load to accomplish the task you're trying to accomplish. Development always has cognitive overhead. Everything has cognitive overhead. An intrinsic cognitive load describes the complexity of that task, the task you're trying to accomplish, and what important information you have to hold on to, the reasoning about how all of that information fits together. There's also extraneous, or sometimes referred to as extrinsic cognitive load, and that's all the other stuff. So that's all the cognitive resources used up by unnecessary tasks, or by excessive complexity, excessive reasoning, the things that don't necessarily fit into what your actual task is. So if, just as an example, and definitely hasn't happened to me, and I'm going to put another I'm lying up there because I'm definitely lying. If your ADHD affects your inhibitive executive process, like I was talking about earlier, and you can no longer have the thing in your head that goes, hold up, that thought isn't important. Let's not do that right now. If your ADHD isn't performing that work very well, then cognitive load, especially extraneous cognitive load, can include things like your cat appearing in your field of vision, and you start to wonder, like, if Hamilton had like a D&D alignment, would he be like chaotic neutral or chaotic evil? Because it could really go either way. It's hard to say. Anyway, so that's a whole train of thought that you could go into, and that's still cognitive load. It's just extraneous cognitive load. And some of us experience that more often than others. Usually, though, the extraneous cognitive load comes when we have to pause, when we're looking at code and we have to like decipher something, or we have to do some quick calculations, just really anything that interrupts us from the middle of our train of logic that we're following. And whatever may be the case, whatever creeps in to tip you into cognitive overload territory, there are strategies to help avoid it, to help avoid diverting your train of thought into like calculations and decoding something, or at least to help you pick it back up easily if you can't help it, if you can't avoid thoughts like, this cat is chaotic. Let me think about that for a sec. So I'm going to start talking about some of these strategies. There's lots of strategies for supporting working memory and for kind of making better use of your working memory. But I'm going to focus on a few here that are directly applicable to development, and establishing a brain-friendly code base. And knowing that working memory is limited to a few chunks, we can make the most use of those chunks. And I'll finally talk about what I'm referring to when I say chunks, because it's a very particular word. Basically, in your working memory, as I've said, you can hold on to chunks of information. And so what you can actually do to kind of supplement your active working memory, the amount that you can hold there, is you can break your information into chunks. And probably the most common example of that is in a phone number. So there's a reason we say like 317-254-8518, which is, I actually just pulled out, and I'm kind of impressed, but also it fits into this talk because that was like my first phone number as a kid, like only in grade school. But there's a reason we remember it with 3 numbers and then 3 numbers and then 4 numbers, in the US at least. Other places do it differently, but it's always in chunks. And that's because you can remember each chunk individually much more easily than you can remember those all as 10 separate digits. So in code, that happens when you kind of combine multiple things that fit into one whole. So that can be like one function or one computed variable or something like that. Those can represent chunks, and they can fit into your working memory and make your working memory capacity larger. We can also work to get rid of extraneous complexity by abstracting away the details. I'm going to kind of breeze through the rest of these because I'm side-eyeing my time and I'm nervous. But we're going to come back to all of them in much more detail. So we want to make sure that we're not wasting memory on unnecessary tasks. We want to keep code organized, keep it tidy, keep it logical. Use comments when necessary. I'm going to kind of touch on that one. In short, we're trying to make things necessary, clear, or make necessary things clear, visible, and available. That is super essential to following logical threads. Finally, we're going to talk about using cyclomatic complexity as kind of a guide to identify where potentially we could alter the code and make it more friendly for working memory. So we're going to look at a sample app that I wrote. Again, sorry for these screenshots. They're not the best. And I'm gonna use this to demonstrate the principles that I'm talking about. So I wanted to make an app that had limited scope, that was feasible to write in its almost entirety before I gave this talk, but also something that I would return to later. And this was really essential because it meant that I would have to keep future Jill in mind. And future Jill is going to benefit a lot from these working memory tactics. So I just started playing a tabletop RPG that uses the fate system. Kind of curious if anybody has used the fate system. Oh, okay, got a couple. Sweet. So you don't have to be familiar with Fate or like with role-playing games like D&D to understand what's going on, because it's a pretty straightforward app. I'm going to point out a couple features. So we land on the character screen. It just has a list of characters, ones I've created in the past. And you can add or delete characters. There's also like 2 subsystems of Fate, core and accelerated. There's more subsystems. All of that unimportant. Just know you can add, delete characters. When you tap on one of these characters, it takes you to the character kind of profile. So this is like your character sheet. This is where you can edit your name, your description of your character, various points, aspects, some other random stuff in the Fate system. But I want to point out the skills section. And it's actually super hard to tell, but it's actually a horizontal scroll view. And it just cuts off really well. So I'll work on that. But point is, what the skills section is doing is super minor validation. And the validation it's performing is twofold. One, you can't have duplicate skills. So I don't know if you can see it, but there's 2 investigate skills, and the font is red because you're not supposed to do that. There's also 2 deceive skills. You're not supposed to do that. Those are red also. There's one more piece of validation it's performing. It's not beautifully done, but again, this was a time-constrained thing, so maybe I'll come back to that. It's checking that we're conforming to what's called like the skill pyramid. And so what the skill pyramid means is there's 5 different levels of skill. There's superb, great, good, fair, and average. And you can't have more skills in superb, for example, than you have in great. You can't have more skills in great than you have in good, etc., all the way down to average. Average is supposed to be, you're supposed to have the most skills in average and the fewest amount of skills in superb. So that's what that validation is doing. That little text next to the superb level is just saying the number of skills in superb, the number of superb skills, is greater than the number of skills you have in the row below. So you can clear that validation, that text by just deleting some superb skills. This is going to be relevant in the slides to come. Okay, so I just want to also point out that the strategies I'm going to talk about can be used at kind of a greater level, like a level at a greater scale. But ultimately, everything's going to come down to a macro level when you're employing these strategies for working memory, because it's the code at a macro level that can throw you off and that can throw you into cognitive overload very easily when you're following a train of logical thought. So this is the code that we're going to look at. This is a really small piece of what is already a small app. But there's already a lot of things that we can look at in this small piece of code. We may not experience cognitive overload here, but it's certainly effortful to decipher. You can't just read through this and understand it. I don't know what this property does or gives me at a glance. And that's me personally, and I'm the one that wrote this code, and it was like 2 weeks ago. So I'm guessing that you as the audience, unless you can like just absorb it, you probably don't know at a glance what it does either. So imagine trying to make a change somewhere in this app, and I'm quickly running out of time, so I'm gonna skip all the things that come into play when you're finally arriving at something like this. But imagine you're following some kind of train of logic, some kind of spatial logical thread that gets you here, and you have to keep all this other stuff in mind. You can experience cognitive overflow really easily when you arrive at something like this that you can't decipher with any degree of ease. And if that doesn't intimidate you, then I'm gonna kind of frame this in another way. So I don't know why this would be the case, but just imagine that this code happens to be embedded in like a map that's in a function that returns any publisher, and that is like chained with a bunch of other any publisher functions that's in some like API, that's in like a login flow that has infinite ways of going through that login flow, and like 12 API calls, and it's all madness and insanity, and then you arrive at this thing and you cry because your brain is goop. That is cognitive overload. That is what it is, and we want to avoid that at all costs. So if you think about your tabletop, all the stuff that you're thinking about, all the contextual information you have about this project, and all the like I said, all the threads that you followed to get here, you have to like basically sweep it off the table and put all of these pieces onto your table to start deciphering. So what I'd like to do is kind of take some steps through this computed property to arrive at something that's easier to decipher with your working memory limitations. So I'm going to talk about naming. I'm going to breeze through this one because I'm getting close. So we're going to talk about naming that's consistent, doesn't give false impressions, is accurate, and is descriptive. I'm going to go into the differences between those because they're super related. But let's start with consistent naming. So I put in parentheses the part that is kind of the earlier goals of our cognitive strategies that I talked about a minute ago. So this one and a lot of these are going to be don't waste working memory on unnecessary tasks. In this case, don't use multiple variations of the same name to refer to the same kind of information. I also wanted to point out that a lot of these are going to be very, very familiar strategies because, you've probably read some books like Clean Code, or you've been a developer long enough to know like what the rules are for naming. But I still think this is really important because we're looking at it through the lens of working memory. And looking at it that way, we're kind of reminded of why it's so important to think about these things consistently, to not kind of drop the ball and be like, I'll figure this out later. It's important to stick with them. So again, don't use multiple variations of the same name to refer to the same kind of information. So in our sample piece of code, we have error skills and skills with errors. I can probably guess that these are referring to the same thing and that they're just poorly named. And we can kind of double down on that when we see that it's actually returning skills with errors. So even if we don't know what this does, we know that there's some inconsistent naming happening. I'm sorry that I'm breezing through this again. I'm just going to choose error skills because it's synced. Boom. Also, avoid names that give false impressions. So in Swift, there's things that actually mean something really specific, obviously. One of these things is error. Error is a type. So when we look at this, we might be looking for an error type. We might be looking for that, but we won't find it, and that's a cognitive trap. We don't want to continue to have to sift through that the next time we look at this computed property. So I don't want to name it error skills. That gives a false impression. That wastes even small cognitive resources. It wastes them. So I'm going to call these invalid skills. The second thing, I'm out of time. Okay, do you mind if I breeze through this in like 2 minutes? I'm going to do it. Okay. Use accurate naming. So it's important not only to make sure that you're not using the wrong kind of information, but also make sure you're using the right kind of information. So in this case, invalid skills, if you look at the actual return type or the type of this property, it's skill level. So we might have to think about, is this actually returning skills or is it returning levels? Spoiler, it's returning skill levels. It's improperly named. So we rename it invalid skill levels. Use descriptive naming, not just about what's wrong, not just about what's accurate, also about giving enough information. So we're going to return to this again. Oh wait, false. We're going to go to two new things. So these are skill counts and skill levels. These are accurate. They're both giving us counts and levels, or they're each giving us counts and levels, and they're not using any reserved Swifty words. But so what? So what skill counts? What is it actually telling us? It's not just some arbitrary list of counts and some arbitrary list of skill levels. It's giving us something, and so we want to be able to see that at first glance. So renaming it skill counts by level and all skill levels tells us exactly what we're looking at. We're looking at skill counts for each level, that superb, the great, the good, the average, no, sorry, the fair, and then the average. And then all skill levels is actually referring to an enum and each level within it. So this is a lot easier to read. The other thing I want to talk about, I'm going to skip this mostly, extracting complex logic into functions. So like I said, we want to chunk information. That's huge. We also want to be able to just read the function, read the original computed variable. And if we use functions, then we can use function names that tell us what that thing is doing. Basically, we want to get this as close to reading a kid's book as possible. So if we do a couple extractions here into two functions, now we can see what this is doing a lot better. So basically, I've extracted this into get skill counts by level. And if we look at get skill counts by level, we can see that it is calling get skills for level. No, I'm not really giving enough details for this to be helpful, but the extraction is the important thing. Abstraction is good, extraction is good. Create variables where it adds clarity. I will post these slides, provide comments. That one's problematic for some people. I know there's a lot of anti-comment purists. Comments are great sometimes, and I want to stress that. I should actually go back, but in certain cases, comments can really clarify your logic, especially providing contextual project information that the dev isn't otherwise going to have. You don't want the dev to have to go and look back at the documentation and look at maybe a past feature ticket to find the acceptance criteria. that had to happen. So I have an example of that. The next thing, this is the last thing that I really want to touch on, and that's cyclomatic complexity. When I was kind of a baby dev and I saw like SwiftLint throwing the cyclomatic complexity warning, I was like, oh, that sounds intense. And so usually we just ignore it. Now I get it. It's super straightforward, as it turns out, at least the definition we're going to work with. So we're just going to call it the number of checks or decisions the code has to make, plus 1. So 1 is the base code with no like ifs, no optionals. And then for every if or optional or try or whatever, we're going to add 1. So the code now that we have finally arrived at after doing all the things that make it consumable by working memory, now it has a cyclomatic complexity of 2, which is great. That's consumable. You can look at this, you can see what it does. There's only 1 check that you have to kind of account for in working memory. I have this whole other view that's an atrocity because I haven't gone back through and used these strategies on it yet. But this actually spans 2 slides. You can see there's 4 checks here, there's 5 checks here, and then the 1 for kind of the base code. So this has a cyclomatic complexity of 10. This should be kind of an indicator to you that it might be time to go back through this code and extract some stuff. To put it, in this case, into extracted views or into your view model or your model as your architecture dictates. And to make this more consumable for your working memory. That's what cyclomatic complexity is. It's really helpful for seeing like where you can still do work to make your code simplified. It's not always the perfect rule, but it's going to be helpful in identifying this, for example, is super hefty. So make it handleable, make it humane, make it fit into your working memory, and then you'll be golden. So working memory, for all its quirkiness, is at the heart of understanding what humane development is. We're kind of now hopefully better equipped to answer the question, what is humane development? It's remembering the humans that are going to interact with the app at every level. It's about having compassion for the people consuming the product at the final stage, the product itself, but also as the work in progress. It's being inclusive and inviting people to share in a conversation that's based in code. And it's being kind to yourself. It's accepting your own limitations and the limitations of those around you. Humane development is about accepting us all as imperfect humans and then allowing us to participate in creating something anyway. As I mentioned previously, I have ADHD, the predominantly inattentive type, and sometimes I just have to accept that ADHD brain has the wheel today and do my best to mitigate the fallout. That might be why this talk and this subject is so close to my heart. It's also why I named the talk the way that I did. So this has been ADHD, a discourse in humane development. Thank you. I'll answer questions on Slack. I'm so sorry that I breezed through the last bit. Yeah, feel free to hit me up or seek me out anywhere.